Okay, in this lecture, so third lecture out of chapter 14. So in this lecture, we'll look at the reactions of ethers. So ethers are very commonly used as solvents in organic chemistry. So what would be some ideal properties of a good solvent? Well, one thing to consider is a boiling point. So at the end of the reaction, you have to get rid of the solvent. So having a low boiling point can be a useful feature of a solvent, so that's easy to remove. Doesn't require too much energy, because if you have to heat it up, then you have to use a lot of energy to remove the solvent. That can have a downside too, though, because if it is a low boiling point, then you're going to have a significant amount of solvent in the air at any one time. So that creates more of a lab hazard and some environmental hazard, I guess, if your solvent is constantly evaporating off. They must be relatively unreactive, because whatever you're using as a solvent, you don't want it to interfere with the reaction that you're doing, obviously. And ideally not too expensive. So the two most commonly used solvents, right, diethyl ether and THF, are not too expensive. So obviously if you're going to have to use a lot of solvent, you don't want it to be very expensive. And ideally low toxicity. So these two ethers are relatively safe compared to some other solvents. So with minimal exposure, not really a toxicity issue. They do have downsides, ethers do though. They are flammable, and they can form explosive peroxides, as we'll talk about. Okay, but since they are not very reactive, we're not going to cover very many reactions of them. There's just not a lot of reactions that ethers undergo that are useful synthetically. So we'll only look at a couple of reactions, actually. So one reaction that we'll look at is how ethers react with HX. So HX, so HBr, HCl, or HI. So if you take an ether and you would need two equivalents of HBr or HCl or HI, then these are the products you make. You make the two alkyl bromides and you make a water molecule. So predicting the product is easy if you just learn to think about these reactions. So you're basically going to lose a water molecule, and then you're going to stick a bromine here, and you're going to stick a bromine there, and that's your products. All right, but let's look at the mechanism. How does that reaction work? So in this case, it does matter whether the ether is at a primary, secondary, or tertiary carbon. Because it's a primary, it's going to undergo SN2-like reaction there, or if it's secondary or tertiary, then it's going to undergo an SN1-like mechanism at that side. Okay, so the first thing that's going to happen is you're going to protonate the oxygen with whatever HCl, HBr, HI you're using. You're going to protonate the oxygen first. And basically that's converting the oxygen into a good leaving group, right? Because now it can leave as an alcohol. So if Br minus attacks, then if it attacks this carbon, it's going to do so in an SN2 fashion and kick off a cyclohexanol. So since that's at the primary carbon, that's going to be SN2. Right? If it's SN1, it would have to make a primary carbocation, which is very unstable. So this will undergo an SN2 at the primary center instead. So that gives you one of your products. There's the 1-bromopropane. And now you have cyclohexanol, which was a leaving group in this reaction. Well, we have looked at in previous chapters that alcohols react with HX. So as soon as you make the alcohol, it can react again. So take a lone pair of electrons on the alcohol, oxygen, make a bond to hydrogen. Now you have a water molecule, so now you've converted the OH into a good leaving group. And since this is secondary, water can leave, and you can make a carbocation. Which means you would have to look out for rearrangement if this could potentially rearrange. In this case, there's nothing to rearrange to, so you just make the carbocation, and then in the next step, the Br minus attacks, and there's your second product. Now, well, technically third product, because water would have been a second product formed, and then the third product formed is the other alkyl halide. Okay, so again, you just have to keep in mind, if you're working through the mechanism, if the carbon's primary, then the halogen is going to, or halide is going to attack the carbon and kick off the leaving group SN2-like. If it's at a secondary or tertiary carbon, then it's going to go carbocation intermediate instead. Or something's going to leave to make a carbocation, and then the halide is going to attack. Okay, so if we took this ether, so it's a little bit more complex example, but same basic principle. If you learn to recognize the reaction, you can just recognize you're going to lose water there, right? And then Cl minus is going to end up here, and Cl minus is going to end up there. But let's work the mechanism so that you can see how this works again. Okay, so you would protonate first. And then it doesn't matter if you do, so this is going to be at a tertiary center. So SN1 like there, and this is at a primary center. So SN2 like here when you do the mechanism, and it doesn't matter which one you do first. So let's let Cl minus attack. So attack here, kick that off. And then protonate again, so another HCl. And then water leaves. Oops, sorry, lost the methyl group. And then Cl minus attacks. And then your final product would be, let's see, 1, 2, 3, 4 carbons. 1, 2, 3 would be, that would be your major organic product, right? Okay, so another reaction that ethers undergo is they react with oxygen in the air. So you would typically see oxygen Lewis structure drawn like that, but this is the diradical form is, so if we took this double bond and let each oxygen have its electron back, and you have a diradical, that better represent the way oxygen actually reacts. So what's going to happen in this reaction is it's going to pull off a hydrogen atom on the carbon next to the oxygen, so either side. And then that would make this peroxyl radical and this carbon radical, and then those two can react with each other to make an oxygen-oxygen bond. And now you have a peroxide, right? So a peroxide is an oxygen-oxygen bond, so that would, let's see, so that would be a peroxide bond. So not so useful synthetically necessarily, but this basically represents a lab hazard because peroxides, this is explosive. So this can particularly be a problem if you're trying to dry your ether and you want to distill. So if you want to distill your ether off, so if you had a boiling pot and you have diethyl ether here, well, it's going to have some peroxide in it. And so if you did a distillation, well, the ether will distill off, but the peroxide won't. So the concentration will build. And if it gets too concentrated, then it becomes an explosive at that point. So there have been many instances of peroxide stills exploding because the proper precautions weren't taken to make sure there are no peroxides in there before the distillation was done. So any ether, it doesn't matter how many carbons are attached, but the position next to the oxygen in the ether is susceptible to oxidation to make a peroxide, and then that's where the lab hazard comes into play. Okay, so that's it for the reactions of ethers that you have to know.